Hi, everyone. Today we're going to continue our section 3.2 lecture. So this is part 2. So we have mostly looked at how polynomials work at their vertexes. Now we're going to look at how polynomials work as x gets really big or really small. So we're going to use some notation for this. So arrow notation is what it's called. So we have as x goes to infinity and as x goes to negative infinity. So some examples of what this means. For y equals x squared, y goes to infinity as x goes to infinity, and y goes to infinity as x goes to negative infinity. And then for y equals x cubed, y goes to infinity as x goes to infinity, and y goes to negative infinity as x goes to negative infinity. All right, so we have these two terms, even and odd polynomials. And this will make a lot of sense once we write out exactly what this means, their name. So if we have a polynomial, p, and if it's an odd degree polynomial, there are two possibilities for end behavior. So basically an odd polynomial is a polynomial of degree of an odd number, and an even polynomial is degree of an even number. So if there's an odd degree polynomial, there are two possibilities for end behavior. And what we mean by end behavior is we mean as x approaches positive or negative infinity. So for our two options, option 1 is if we have something kind of, I kind of just have dotted this inner area because there could be as many like ups and downs as needed for depending on the degree of the polynomial, but the big part is about the end behavior. So this y approaches negative infinity as x approaches negative infinity. And I might drop the as sometimes, but we can kind of get from context that it's y is dependent upon x because that's what we've always used. And then y approaches infinity as x approaches infinity. So this behavior here is when the leading coefficient is positive. This means that the coefficient on our highest value or highest power exponent, it is a positive number. So that makes these conditions hold. And then the other option for 2 is the opposite of this. So y approaches infinity as x approaches negative infinity, and y approaches negative infinity as x approaches infinity. Right. And this case happens when the leading coefficient is negative. So this is why our leading coefficient was so important and why we stressed it in the first lecture, was because it determines the end behavior of our polynomials. All right, and now we have the even case. So if P, our polynomial, is an even degree polynomial, there are two possibilities, again. So our first one, we have our graph here. So here, y approaches infinity as x approaches negative infinity. And over here, y approaches infinity as x approaches infinity. And this happens when the leading coefficient is positive. And then the second result is when we have a graph like this. So here, y approaches negative infinity as x approaches negative infinity, and y approaches negative infinity as x approaches infinity. And this happens when the leading coefficient is negative. All right, so those are our four cases for end behavior, 2 for odd and 2 for even. And then we have some examples we can show. So our first one will be when y is 7x to the fourth minus 3x squared plus 4x minus 1. All right, so here our leading coefficient is positive. And it's an even degree, so it's an even polynomial. So this means that y approaches infinity as x approaches infinity, and y approaches infinity as x approaches negative infinity. All right, and then our next example, we will have y equals negative 4x cubed plus 7. So this is an odd degree, and our leading coefficient is negative. So this means that y approaches negative infinity as x approaches infinity, and y approaches positive infinity as x approaches negative infinity. So these are our end behaviors. So now we're going to move on to a different topic, and we're going to focus on the zeros of polynomials. All right. So we're first going to define what a zero is. All right, so if P is a polynomial, then C is called a zero of P if P of C equals 0. So C is a solution to P of X equals 0. And then note that on a graph, we call such C's our x-intercepts of our graph P. So this is the big idea of what this section is about, or with the zeros at least. All right, so if P is a polynomial, and C is a real number, then the following are equivalent. So 1, C is a 0. 2, x equals C is a solution of the equation P of x equals 0. 3, x minus C is a factor of P of x. And then 4, C is an x-intercept of the graph P. So this here is very important. All right, so let's do an example. So let's find the zeros of this function. P of x equals x squared minus 5x plus 6. All right, so let's first notice that minus 2 times minus 3 equals 6, and minus 2 plus minus 3 equals negative 5. That means that we can factor. So x squared minus 5x plus 6 equals x minus 2 times x minus 3. There we go. All right. Therefore, x equals 2 and x equals 3 solve P of x equals 0. Thus, 2 and 3 are zeros for P. All right, and remember when we have something like this, where there's factors multiplied, as long as just one of them equals 0 makes the whole equation 0. So that's why both of these are 0. Because if we plug in 2, we get a 0 times a negative 1. And if we plug in 3, we get a 1 times 0. And both of those become 0. All right. So then we have an important result for this section. It's the intermediate value theorem. All right, I'm going to state the full theorem, and then I'm going to sketch an idea that will be probably more helpful than the actual theorem. Just kind of knowing how to use it is very useful, though. All right, so P is a polynomial. And P of A and P of B are of opposite signs. Then there exists at least one value, C, between A and B, such that P of C equals 0. All right. So the idea behind this is that if we have a graph and we have A, and we have B. I'm going to say that P of A is negative, and P of B is positive, and they're part of a polynomial. That means, I'm going to make the graph red, that at least one, in this case I drew 2, there exists zeros between. Because think about it, the simplest graph we could have in between PA and PB is just a line, and a line is still a polynomial. So even if we just had a line, there's going to be at least 1 0. And since all of our polynomials, and again, that's part of the conditions, is that we have a polynomial, they are all continuous, which means there's no breaks, there's nothing that's going to just jump in between PA and PB without going through 0. So that means that if you have a negative value and a positive value as outputs, at some point you have to have a 0. All right, so now we're going to go through some guidelines for graphing polynomial functions. All right, so there's going to be 4 steps that I think are the most important when going through graphing a function. So 1, the zeros. So you'll want to factor the polynomial to find all of its real zeros. So these are going to be our x-intercept. And remember from earlier, they have to be the real zeros. And then 2. We're going to do some test points. So we want to make a table. All right, so once we make a table of these values, we're going to choose points outside and between our zeros. Okay, so this will let us know if the values are above or below the x-axis. So if we know if we just have like a point that just like kisses the x-axis, or if we have a point that goes through the x-axis and into either like up into the positive area or the negative area. And 3, we need to look at our end behaviors. So we have to determine our end behaviors. So that, remember, that is y as x approaches positive or negative infinity. All right, and then 4 is graph. All right, so here we're going to plot the intercepts. And test points that we found in our table. We're going to graph a smooth, because all polynomials are smooth, curve that passes through all points. And also has the proper end behavior. All right, so let's do an example of how to graph a function. All right, I'm going to start with an already factored function just to make things a little easier for us. All right, so here it's very easy to see that our zeros are 5, -1, and -4. All right, so now we're going to do some test points. So we need x and p of x. You could also write y there if you'd like. I don't really mind if you use p of x, f of x, y. Just be consistent within the problem itself. So I'm going to pick a point to the right of 5 to get a point outside of our 0, and then a point between 5 and -1. I think I'll pick 0 because that's always a nice one, and then a point in between -1 and -4. So let's go with -2. Then a last point is something to the left or even like smaller than -4. So I'll just go with -5. All right, and if we were to plug 6 in, we'd get a 1. I'm just going to do some scratch work. So we'd get a 1 times 7 times 10, so that's 70. We plug in 0, we'll get a -5 times a 1 times a 4, so that gives us -20. We plug in -2, we get a -7 times -1 times 2, so that gives us 14. And then if we plug in -5, we get a -10, a 4 times 4, and a -1. So here we get a -40. So this lets us know kind of the behavior between our test points and our zeros. So, and we also have to notice that this is a third degree polynomial because there are 3 x's that get multiplied. So it's just our scratch work, kind of the side. So this is a third degree polynomial. And then notice that it's positive x times positive x times positive x. So that means it has a positive leading term. So this implies that y approaches infinity as x approaches infinity, and y approaches -infinity as x approaches -infinity. All right, so now that we have our zeros, our test points, and our end behavior, we should be able to graph this. So if we draw our axes, and we start with I'm going to let this be -5, -4, -2, -1. We all know 0. And then we have a 5 and a 6. So we know our zeros are at, I'm going to make our graph red again. Our zeros are at, are at -4, -1, and 5. And we know our points at, and then our y-intercept is also our point at 0, which was -20. We're going to say that this here is -20, and this is -40. This is 14, and this is 70. It's okay if your graphs aren't perfectly to scale. I don't expect them to be because sometimes you'll get things like this where they go really tall, really fast, and we haven't gone very wide out. So as long as you label things clearly and they kind of make a decent amount of sense, that's all I'm really asking for. All right, and we know that y approaches -infinity as x approaches it, and it approaches positive infinity as x approaches positive infinity. So those are going to be our end behaviors. And then our test point at -2 is at 14. At -5 is at that should be a 40, not a 4. And then at 6 is at 70. And now we just kind of connect the dots. Forgot to draw a little point at 20, but it went through there. So that's our graph. It's an approximate graph, and the most important part of a graph is not to be perfectly accurate. It's just to give you a strong idea about what's happening so you have a good intuition about what your function should be doing. So there we go. All right, now we're going to go over one last thing before we end the lecture. We're going to talk about local maxima, which I'll just usually write max, and minima, which we'll usually just write min, max and min. We all know those terms. All right. So if we have a graph, and we have an A and a B, so A, f of A, is the local max, because if we just look in a little rectangle around A, or f of A, and f of B, if we just look in this little rectangle, it's the largest point there. Same with B and f of B is the local min. So yes, so if we look in these viewing rectangles, A is the largest number and B is the smallest. So that's what it means by local, is it means within a little window. Because you know polynomials, as they go to infinity, they either go to positive or negative infinity. So those will be our like global max and mins. All right. And this is a useful fact to know about polynomials. If P equals an xn plus an minus 1 xn minus 1 all the way to a1x plus a naught is a polynomial of degree n, then P has at most n minus 1 local extrema. All right, and what extrema means, this is max or min. It's just the extreme points of your graph. It's just a way of saying it has at most n minus 1 local mins or maxes. Because math people like to add some fun words to sound extra smart when they're doing it. So they couldn't just say max or min. All right. So this is our last lecture for section 3.2. So our next lecture will be for 3.3. See you then.